Welcome to lecture series in physics. In this lecture series, we are discussing welcome to UGC lecture series in physics. In this lecture series, we are going to discuss about gravitation. So, the following contents are to be discussed in this episode. First, I am going to discuss about equipotential surface, and the second topic will be on gravitational potential and field due to a spherical shell, and the third topic will be on gravitational potential and field due to a solid sphere, variation of g with latitude or rotation of the earth, and variation of g with altitude. So, these are the following topics I would like to discuss now. So, let us now turn our attention to discuss about equipotential surfaces. So, what do you mean by equipotential surface? So, if the gravitational potential is same at all points on the surface, and such a potential is called equipotential surface. So, surface at all the points of which the gravitational potential is the same is called an equipotential surface. So, for example, you consider a spherical surface around a point mass with the mass as the center is also known as the equipotential surface. Since the potential on the surface is constant, no work is done against the gravitational force in moving a unit mass along it. So, we will discuss about the gravitational potential and field due to a spherical shell. So, there are number of cases. First, we will discuss the case where the point is outside the shell. You consider a point P outside a spherical shell at a distance r from the center O, and let A be the radius of the shell and rho be the mass per unit area of the surface of the shell, and m is the total mass. So, in the diagram you join OP is equal to y, and you consider a thin slice of the shell contained between two planes AB and CD drawn close to each other at right angles to OP. Join O and A, O and C, A and P as shown in the diagram. So, let us say angle AOP is equal to theta. This is AOP is theta, AOP is theta, and AOC is d theta, and this is AOC is d theta. So, angle AOP is theta and angle AOC is d theta. So, AE is the radius of the slice. Here A is here and this is E, this AE is the radius of the slice, and this radius of the slice is nothing but it is A into sin theta. So, we will calculate what is the circumference. The circumference of the slice is, it is 2 pi in this into radius. Therefore, it is 2 pi into radius or 2 pi into AE. So, from AE we know that AE is A sin theta. You substitute, you will get 2 pi A sin theta. So, the width of the slice is A d theta, hence the surface area of the slice is 2 pi A sin theta into A d theta. So, when you multiply this A and A, it is A squared and it is 2 pi A squared sin theta d theta. So, what is mass? The mass of the slice is surface area of the slice. The mass is surface area of the slice into density. So, if the density is rho, then I can write the mass of the slice is mass is equal to 2 pi A squared into rho sin theta d theta. Let Pa is equal to x. So, you refer to the diagram. So, this is P, this is A, this value is x. So, let Pa is equal to x, and you take every point and the slice equidistance from P. So, therefore, we will calculate what is the potential at a point P due to the ring. The potential at a point P due to the ring is dV is equal to G 2 pi alpha into 2 rho sin theta d theta by x. So, to find the value of x, you consider the triangle OAP. So, this is the triangle OAP. So, you consider this triangle OAP. So, in the triangle OAP, we know that x squared is equal to a squared plus r squared minus 2ar cos theta. So, you are differentiating this equation. So, when you differentiate, so in place of x squared, when you differentiate this, you will get 2x dx. So, you have 2x dx and a squared is a constant. When you differentiate a squared, it is 0, and when you differentiate r squared, it is 0, and when you differentiate 2ar cos theta, it is 2ar. The differentiate of cos theta is, the differentiation of cos theta is minus sin theta. So, the differentiation of cos theta is minus sin theta d theta. Already you have a minus sign here, and already there is a minus sign here. Therefore, it is 2ar sin theta d theta. Therefore, 2x dx is equal to 2ar sin theta d theta. So, from this we will calculate what is x. So, x is, it is ar sin theta d theta by dx. You substitute the value of x in this equation 1. You substitute in this equation. When you substitute in this equation, we get dV is equal to minus 2 phi alpha rho g by r into dx. And if the entire shell is split up into slices, then the limits or the boundary conditions will be from r plus a to r minus a. Therefore, the potential due to the entire shell can be obtained by integrating the equation from r minus a to r plus a, r minus a to r plus a. When you integrate this, and you will get 4 pi a squared rho into g by r. Now, we know that 4 pi a squared rho is nothing but it is the mass of the shell, and the gravitational potential is V is equal to minus g m by r. Therefore, this potential is the same as due to the mass m at O. Hence, the mass of the shell behaves as though it is concentrated at its center. Now, let us discuss the second case, that is the gravitational potential and field due to a spherical shell, where first we have discussed the case, the point is inside the spherical shell. Now, we are going to discuss the point on the surface of the shell. In order to derive an expression for the point on the surface of the shell, you consider a point which lies on the surface of the shell itself. So, the limit is from 0 to 2a, and you integrate from it is 2 pi alpha by r into rho g into dx. And when you integrate, these are the substitutions, and you put r is equal to a, and when you put r is equal to a, I get V is equal to g m by a. And we will discuss the case point inside the shell. Let a point P be situated at k inside the shell such that OK is equal to r, and therefore, the limits will range from alpha minus b to alpha plus v. Therefore, the points at k is alpha minus v plus alpha plus v. When you integrate, you get it is minus 4 pi a minus 4 pi alpha 2 into rho g, and multiplying dividing by alpha and v, we get minus 4 pi a 4 pi alpha rho g by a is equal to minus g m by a, and v is equal to minus g m by a. Hence, the potential at all the points inside a spherical shell is the same and is equal to the value of the gravitational potential on the surface. And let us now discuss what do you mean by gravitational field. The gravitational field is nothing but it is the gradient of potential, or it is given by F is equal to dV by dr. Therefore, at a point outside the shell, we have V is equal to minus Gm by R, and when you differentiate this, d by dr minus Gm by R, and when you differentiate 1 by R, it is minus Gm by R squared. So, this negative sign indicates that force is towards the center 0, and we will show what is the point on the outer surface of the shell, and you put R is equal to alpha in the expression 1, we get the intensity of the gravitation field at a point on the surface of the shell is F is equal to minus Gm by A squared. At a point inside the shell, the potential is a constant, therefore, F is equal to dV by dr is equal to 0. Let us now discuss the gravitational potential and the field due to a solid sphere. So, let us consider a point P, and this point P is outside the sphere at a distance r. So, this is the sphere, this point P is outside the sphere. So, let us say from here to here the distance is r, and let this center be O, and let m be the mass of the sphere and A be the radius and rho be the density. And you can say you imagine that this is a solid sphere, and this solid sphere is imagined to be made number of large concentric circles. Therefore, we will derive an expression for the point outside the sphere, and each one of the shells produces a potential at a point P outside the shell, as if the entire mass is concentrated at the center O. Therefore, the potential P due to a shell is given by minus Gm by R. Therefore, the potential outside due to the sphere is, it is V is equal to minus sigma Gm by R, that gives rise to Gm by R into sigma m, where sigma m is the mass of the solid sphere, and when you substitute sigma m to be capital M is the effective mass, m1 plus m2 plus m3 it goes on, then I get V is equal to minus Gm by R. And to derive an expression for the points on the surface, you put R is equal to A in the expression, and when you put R is equal to A, we get minus Gm by A, and we will derive an expression for the point inside the sphere. So, in order to derive an expression for the point inside the sphere at a distance from the center O, you imagine the solid sphere to be cut into number of series of concentric circles of radius r, and you can also imagine that hollow sphere is made up of concentric circles. Therefore, the potential at a point P due to the whole solid sphere is given by the expression, that is the mass of the sphere is 4 by 3 pi r cube rho, because mass is nothing but it is volume into density, and this is the mass. So, the volume of a sphere is 4 by 3 pi r cube, the density is rho, therefore, we have 4 by 3 pi r cube rho. Therefore, we will calculate what is the potential at a point due to the inner sphere. Therefore, the potential at P due to the inner sphere is V1 is equal to minus G into 4 by 3 pi r cube rho divided by R, that is equal to minus G into 4 by 3 pi r cube rho. And you consider one such shell of radius x and thickness dx. Therefore, the point P lies inside the spherical shell, and the mass of the shell is 4 pi x square dx into rho. Therefore, the potential at this point due to the shell is minus G into 4 by 3 pi r cube rho by x is equal to minus G into 4 pi x dx into rho. Therefore, the potential is can be obtained by integrating this equation from r to a, and when you integrate you get minus g 4 pi rho into a squared minus r squared by 2. And in order to determine the potential at P due to all the outer shells, we can calculate the effective potential. So, the effective potential is V 1 plus V 2, where V is equal to effective potential. The effective potential is V 1 plus V 2, and when you do this, the effective potential turns out to be minus G into 4 by 3 pi rho into 2 r squared plus 3 a squared minus 3 r squared by 2. When you simplify this expression, it gives rise to minus G into 4 by 3 pi rho into 3 a squared minus r squared by 2. And you multiply and divide by a cube and substitute 4 by 3 pi a cube rho is equal to m, and finally you will get V is equal to minus G m into 3 a squared minus r squared by 2 a cube. And what is the potential outside the sphere? And in order to calculate the potential outside the sphere is given by V is equal to minus G m by r. So, in place of V you substitute minus G m by r. When you differentiate, you will get minus G m by r squared. And for a point on the surface of the solid sphere, you put r is equal to a, and therefore, f is equal to minus G m by a squared. And for the point inside the sphere, the potential at a point inside the solid sphere at a distance r from the center O is V is equal to minus G m into 3 a squared minus r squared by 2 a cube. And we will derive the intensity at the field P. The intensity at the field P is given by F is equal to minus dV by dr. So, minus d by dr. In place of V, we already derived this expression. It is minus G m into 3 a squared minus r squared by 2 a cube. When you differentiate this, you get minus G m by a cube into r. Thus, we can see the intensity of the gravitation field at a point P inside a solid sphere is directly proportional to the distance of the point from the center of the sphere. And we will solve a problem: with what velocity should a body be projected vertically upwards from the surface of the earth, so that it may first attain a height of r by 2, where r is the radius of the earth. You take the radius of the earth, r is equal to 6.4 into 10 power 6 meter. At the surface of the earth, at a distance of r from its center, the potential energy of the body is given by, that is minus m g by capital R. So, therefore, when you do this simplification, I get it is minus m g r squared divided by r. So, that is equal to minus mgr, because we know that mg is equal to g r squared. Therefore, at a distance of r by 2 plus r, or we can, when you simplify this r by 2 plus r, we will get as 3 by 2 r from the center of the earth. Therefore, the potential energy of the body is minus, it is mmg divided by 3 by 2 r. So, when you simplify this, we will get 2 by 3 mg r. Therefore, we will calculate what is the increase in potential energy of the body. So, the increase in potential energy of the body is, it is minus 2 by 3, it is mg r minus of minus mg r. So, when you simplify, you will get as 1 by 3 m g r. And so, if V is the velocity if V is the velocity of a projection, therefore, its kinetic energy, where Ke is the kinetic energy, the kinetic energy is given by the expression, it is half mv squared. So, therefore, we already derived in the last slide, that is equal to, it is 1 by 3 mgr. Therefore, we will find what is the velocity. The velocity is, it is root of 2 by 3 into gr. You substitute all the values, it is root of 2 by 3, g is 9.8 and the radius of the earth is 6.4 into 10 power 6. So, when you simplify, the velocity turns out to be 6469 ms power minus 1. So, therefore, this is the velocity, that is the velocity is 6469 meters per second is the velocity that a body should be projected vertically upwards from the surface of the earth, so that it may first attain a height of r by 2, where r is the radius of the earth. So, let us now discuss the variation of g with the latitude or rotation of the earth. So, in order to derive an expression, variation of acceleration due to gravity with the latitude means it is nothing but the rotation of the earth. So, we will assume the earth is uniform sphere. So, this is the uniform sphere. So, the earth is a uniform sphere and let r be the radius. So, let this r be the radius of the earth revolving about its diameter, in the diameter is north south, and you consider a particle of mass m on the surface of the earth at a latitude lambda. So, this is the latitude lambda, and if the earth is at rest and you can say a particle of mass m is placed at a point P, will experience a force mg along the radius PO towards O. So, therefore, let omega be the angular velocity of the earth, and as the earth revolves, the particle at P will execute a circular motion with B as the center and BP as the radius. Therefore, this BP is the radius, and therefore, what will happen is a centrifugal force will develop, and the centrifugal force acting on P. So, here the centrifugal force will act, and the centrifugal force is, it is mBP into omega squared. So, therefore, I can write it is m into r cos lambda into omega squared, because this BP is equal to r cos lambda, and we can write it is mr omega squared into cos lambda, and the force mg acts along PO. Resolve mg into two rectangular components. So, you dissolve mg into two rectangular components, that is mg sin lambda along PA. So, along PA, so this is mg sin lambda along PA and mg cos lambda along PB. Therefore, PB is, this is PB. So, for this it is mg cos lambda. So, you are resolving into two perpendicular components, mg sin lambda and mg cos lambda, and mg sin lambda is along PA and mg cos lambda is along PB. Therefore, let you represent the net force by PC, then I can write PC is equal to mg cos lambda minus mr omega squared and into cos lambda, and PA is equal to mg sin lambda, and we will calculate what is the resultant force. The resultant force is PQ is equal to PC squared plus PA squared from the diagram. Therefore, we can write mg dash is equal to mg cos lambda minus mr omega squared is cos lambda whole squared. This is one resultant. The other resultant is mg sin lambda the whole squared, the whole power 1 by 2. And when you simplify further, we will get it is mg into 1 plus r squared omega squared by g squared into cos squared lambda minus 2 r squared omega by g into cos squared lambda into 1 by 2. Therefore, mg dash is equal to mg into 1 minus r squared omega squared g into cos squared lambda into 1 by t. You neglect the higher order powers r squared omega power 4 by g squared into cos squared lambda. So, when you neglecting the higher order powers and you simplify this expression, the expression turns out to be mg into 1 minus r squared omega squared cos squared lambda by g. So, therefore, this r omega squared by g is small and its higher powers can be neglected. Therefore, I can write g dash is equal to g into 1 minus r squared omega squared cos squared lambda by g. And therefore, the variation of g with latitude due to the rotation of the earth or rotation of the earth is given by g dash is equal to g into 1 minus r g dash is equal to g into 1 minus r squared omega squared cos squared lambda by g. Let us now solve a problem, and I will read out the problem. How many times then the present speed would the earth have to be rotate about its axis in order that apparent weight of the bodies at equator be 0, and what should be the new period of rotation? So, this is the problem. So, let us summarize what we have discussed so far in this session. Let us now summarize what we have discussed so far in this session. In this session, we discussed about equipotential surface. What is a equipotential surface? What are the conditions for an equipotential surface? And we have given a classical example for an equipotential surface. And also, we derived an expression for gravitation potential and field due to a spherical shell and due to a solid sphere. And finally, we derived an expression, that is the variation of acceleration due to gravity due to latitude or the rotation of the earth. Thank you.